All right, so again, section 2.1, the tangent line problem. One of the motivations for the motivational problems for the discovery calculus, and primarily the Leibnizian perspective. That's a good word, Leibnizian perspective. So here we have a parabola, and it opens down. Kind of looks like if you've ever been to St. Louis, right? This might be a picture you take, right? Maybe you stand down here, right, and you wave with your big hand, and someone takes a picture. You're under the Gateway Arch. Although the Gateway Arch is not a parabola. Did y'all know that? It's the most mistaken parabola in the world. It's actually a catenary curve. And the catenary curve is a little bit different up there at the vertex. Catenary curve is a little bit more like that, a little bit flatter at the vertex. So, but anyway, if you call it a parabola, most people are going to know what you're talking about. But anyway, this is a true parabola. Got a little pointer vertex. And here's the equation of it, 3x minus x squared. Here's what I want to ask you. How fast is the graph of this function changing? And when I talk about the graph of f of x, first of all, we're talking about the y values. So anytime we refer to the graph of or f of x, we're talking about the y values of that graph. So how fast are the y values changing when x is 1? Okay, so this x-axis didn't really come through, but here it is, essentially. So here's x equals 1 right there. And if I go up as straight as I can, somewhere right there, I want to know how fast the graph is changing at that point. Does that question even make sense? Yes, in what respects does it make sense? Yeah, perfect. Yeah, so you kind of already have an advanced notion of what we're looking for, but this graph, first of all, is changing, right? When you have a line, if you think about the x values kind of increasing at a constant rate, sliding from left to right at a constant rate, how fast are the y values changing with respect to x? For a line, the y values go up at a constant rate. That's why you study it in Algebra 1. But the y values here are not changing at a constant rate, are they? They actually start off very steep, so they are going up pretty rapidly, and as they approach the vertex, they are slowing down. The y values are still increasing, but at a decreasing rate. Would you agree? And then as they turn the corner, now my y values are decreasing, and their speed is picking up, okay? And you can imagine maybe this being like a ball. What goes up must come down. And as you throw it up into the air, you know, with the initial velocity, it's going pretty fast, and then it gradually slows down up into the vertex where it turns around, and then it accelerates back towards Earth. So kind of the same idea. But what Galileo was working on is the same thing Newton was working on. Galileo, of course, precedes Newton. They were interested in how fast that ball, or whatever it is that you threw up in the air, was changing, not at x equals 1, but at t equals 1, let's say, seconds. If we let the x-axis now be time. How fast was that ball that was thrown up into the air changing at t equals 1 seconds? In other words, if the ball had like a little speedometer on it, like you do in your automobile, right? And you drive down Ohio after school, and you look down at any given time, and at any given time it's no more than 20, right? Right, because that's where cops like to hang out. It tells you your instantaneous speed, right? That's exactly what they were trying to figure out. At that moment, if that little ball had a speedometer on it, and we look down at it, how fast would that thing be changing? That is, how fast is it going up with respect to how fast it's going to the right? It doesn't make sense in the sense of a curve, because if you remember from Algebra 1 was finding rates of change. And rates of change were computed finding what quantity? You already have that from last year. Slopes, good. So the slope of a line gives you its rate of change. And on a line, again, which is boring, the rate of change at any point on the line is the same as the rate of change between any 2 points on the line, right? Which meant that the slope was a constant, and therefore the rate of change was a constant anywhere and everywhere. But that's not the same here. So now we can kind of redefine the problem as the rate of change of an object at a single point in time is the same as finding the slope of the graph at that point. And so that's the Leibnizian perspective. The instantaneous rate of change, which turns out to be the velocity, if you're talking about how fast something's position is changing, that's the Newtonian perspective. The Leibnizian perspective was finding the slope of a graph. Well, it doesn't really make sense to talk about the slope of this graph at a single point, because as you learned from Algebra 1 again, how many points do you need to even draw a line to even talk about slope? 2. And we're trying to find the slope at a single point. All right, so let's go ahead and do this. And this is kind of, again, going to be what Galileo was doing when he was rolling balls down inclined planes. We're going to have to use another point. We're going to have to, because the algebra of the day is all we have to compute a slope, and we need 2 points. So the points that I'm going to use are the points 1, f of 1. Okay, I'm going to use the point 1 and then f of 1. That's going to be my anchor point, the one I'm interested in. And I'm going to choose another point over here, 1.5, f of 1.5. In other words, a half of a unit away, or if you're thinking about time, it would be a half second away. Well, that turns out to be at the vertex. And now that I have 2 points, I can actually draw a line through there, and we have a line that touches a curve twice. This line is called a secant line, and that's something that you need to know if you don't already. A secant line intersects the curve at 2 points. So if I can find the slope of the secant line, I'm not going to be finding the instantaneous rate of change. I'm not going to be determining how fast the graph is changing at that point. What I will be doing, though, is figuring out, on average, between this point, x equals 1, and 1.5, on average, how the function rose to be from this y value to this y value. That is, if it went at a constant velocity from this point to this point, it would follow the path that is the straight line. But is that how it actually got there? No. It actually got there by going up a little bit faster and then slowing down into there. Okay? But it would be a decent approximation of how fast it's going at that point. Now I have some mathematics I can work with, right? Algebra 1. Because how do we find the slope between 2 points? Very good. So let's go ahead and do that. We're going to say the slope m of the secant line. I'm going to put a little subscript s for secant line. I'll go ahead and write this out too. It turns out that it's going to give me the average rate of change. So there's no harm in doing that. What I'm doing by saying those two things, I'm tying, again, the Leibnizian and the Newtonian perspective together. Because it ends up being the same thing. They were just motivated by 2 different things. Slope of the secant line, Leibniz. Average rate of change, Galileo and eventually Newton. Okay, it's going to be y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Or more concisely, it's the change in y or the change in x, right? Delta y over delta x, right? Y'all recognize that triangle as delta? And of course, delta means what? Change in. So it's the directed distance. It's a measurable distance that is directed, plus or minus. All right, so for me, since I'm dealing with functions, I'm going to say it's f of 1.5 minus f of 1 all over 1.5 minus 1. Now remember, my point that I'm merely interested in is the point 1 f of 1. But I have to use 2 points. That's what the algebra of the day tells me to do. Now, how am I going to evaluate that? Well, I got to plug 1.5 into here, don't I? Is that going to be fun? Sure. It might be a lot of fun. If you want to go ahead and do that, go ahead. While y'all are typing that in, I'm going to go ahead and load my calculator up. Because I want you to see what's happening here. This is kind of planting the seed, the motivation behind what calculus actually is. Not that you're going to necessarily be doing these tedious calculations. And the calculations do become very tedious, especially when you don't have a calculator. Which, of course, you know, Newton and Galileo did not, unless you call their heads their calculators. All right, so here's what I'm going to do. In y sub 1, I'm going to go ahead and type in my function, which is 3x minus x squared. And what I'm doing also by showing you this is modeling kind of what we are going to be doing with the calculator. I'll go back to the big screen view. Might as well, so y'all can see it. Okay, so there it is in y1. Now, that's all I'm going to do is type it into y1. I'm not even going to look at the graph. It doesn't really concern me. I'm going to go to my home screen and do all my calculations from the home screen. So here's what I'm going to do now. I'm going to go ahead and type in what I just wrote on my paper. Okay, it's the change in the y over the change in x. So from the home screen, alpha y equals gets you to your numerator over denominator. If you want to play around or play along, feel free. If not, you can just watch. We'll be doing a lot of this. F of 1.5, where did I put my function f? In y1. So there's a shortcut in the math print to the alpha trace. That's your F4 catalog. There's a shortcut to all your y equals. We put it in y1, so there it is. Now, if you open parentheses and type in 1.5, close parentheses, it treats that like function evaluation. So for the calculator, that's like f of 1.5. So I'm going to type that in there, and then minus f of 1, which I'll do it again. Of course, we might be able to figure out what f of 1 is, just plugging it in. But it's kind of the same idea. We don't really need to know. There's the change in the y's. And I'm going to pretend like I don't know what 1.5 minus 1 is. I know it's 7. Yeah, okay, good. Complete the joke for me. Joke, right? Okay. So this right here is a super important thing throughout the entire year. This is a quotient of two things being subtracted. So guess what we're going to call this? The, not A, but the difference quotient. We're going to call that the difference quotient. It's the quotient of two differences. It's just delta y over delta x. Notice I haven't had to do any calculations. I've just written it on my paper first. That's important. And then I've typed it into my calculator, and I get 0.5, okay? So now I'm going to go back to my iPad and put 1/2, which is the equivalent to 0.5. Now let's see what that means in terms of this graph. Of course, that means that the slope of this secant line is 1/2, but that means then from x equals 1 to x equals 1.5, on average, we went up a 1/2 unit for every 1 we went to the right, or you could say we went up 1 unit for every 2 we went to the right, however you want to interpret it. Since we're only going over a 1/2 unit, you could say that we went up, what, a 1/4? We went up only a 1/4 of a single unit and over a 1/2. They all come out to the same slope of a 1/2. But that's not actually how that happened, okay? So what could I do then? If I was really interested in how fast it was changing at that point, but I have to use 2 points, yeah, this is like, if you're talking about time, this is like a 1/2 second away. And when you have Galileo starting with an inclined plane and a ball, he'll measure its initial height, and he'll let it roll for a little bit of time and measure it again at a certain time in the future. A 1/2 second might be your maximum, ability to recalculate very quickly. Maybe if you're good, you can work it off so that it's only a 1/4 second. But the human eye can only work so fast, and you can only measure things without instruments, fancy instruments, only so far apart. But the idea is, yeah, let's go ahead. If we want a better approximation, let's take a point that we have to use because algebra requires to, a little bit closer. So we're going to use, of course, the point we want, which is 1/f of 1. Let's go ahead and figure out what that actually is. That's the point 1 comma what? That's easy to find without a calculator, right? What's f of 1? Plug in a 1 there, what do you get? 2. Okay. So it's really the point 1, 2. And I'm going to choose another point that's at 1.1. Now I'll use a different flavor here. Let's use green. 1.1 might be right about there. Now in terms of time, that's letting a 1/10 of a second elapse, yes? Secant line. And a 1/10 of a second is very, very, very small in terms of time, in terms of your ability to measure it. But that right there would give me maybe a better approximation of how fast it's changing at the point. So let's go ahead and write it out. We'll say that the slope of this secant line, which is still going to be the average rate of change, I'm going to call rate of change ROC, or abbreviation. It's still the average rate of change over this 1/10 of a second interval. It's going to be the change in the y values, f of 1.1 minus f of 1, or 2 if you want to call it that now, over 1.1 minus 1, or 0.1. I don't care if you do that. This, again, is called the what? We'll label it here. The difference quotient. And remember, this class and AP in general, and math in general, is not just about coming up with the right answer, but being able to clearly communicate your results. And showing the difference quotient is one of those important things that you need to be able to show to communicate what you're doing. Even though 1.1 minus 1 you could easily call 0.1, it doesn't illustrate really what you're doing. Okay, so from here I could just go back to the home screen, and with the math type you can either scroll up and grab it and hit enter again, and then come back and change the 5s to 1s. You could do that, or you could just type it in again. I have to scroll with my mouse, which sometimes is a little bit frustrating. So it's using the same function, but now at 1.1, and you get 0.9. So that's 0.9. So interpreting that then, of course, that is the slope of this green line, let's go ahead and write it on there. M is equal to 0.9. The other one was equal to 0.5. So is it reasonable that the slopes appear to be increasing? As we slide the point on the right back closer and closer to the one we're interested in, the line's getting steeper. So the slope is increasing. Yeah, 0.9. So in that tenth of a second interval, that graph on average went up a tenth of a point for every one that was going to the right, or up 1 and over 10. I'm sorry, up 1 and over 9. Up 9 over 10, my bad. Yeah, I'm thinking 0.1, sorry. It's 0.9. Can we do better, though? Sure. Now, if you notice, I am quickly running out of the ability to draw them closer together, and the calculations are getting more tedious. But in theory, how close can we get? Infinitely close. So I'm not going to draw any more after this. But let's say now I want to look at the other point being 0.01, 1.01. So a hundredth of a unit away. I doubt Galileo was able to physically measure a hundredth of a second. But if we draw that, it's going to be so close to that blue line that when I draw it, it almost looks like it's not a secant line at all, even though it still is. Let's go ahead and set up the difference quotient first. Always get in the habit of showing your work on your paper/iPad before you go to any kind of calculator. Oops. There you go. F of 1.01 minus F of 1, all over the change in the corresponding x values. And now from the calculator, if you want, you can also hit second enter, which recalls the previous calculation. And then you can just scroll back. 1.01. I have 2 decimals. Now, of course, if you just want to type 0.01 then that's fine. Now, over here, you probably know this, but if you have to add a character and you don't want to have to retype in everything after it, go to the place where you want to insert the character and hit second, what? Delete. Second delete is your insert. And now I can type a 0, and then I can type my 1, and then I can hit delete. And it goes back to non-insertion mode. Okay, so there you go. 0.99. 0.99. All right, so let's interpret that. That means then that on that 100th of a second, if you want to think about time because you can appreciate it more, on that 100th of a second interval, that graph went up 99 hundredths of a unit for every one that went to the right. And you can see that the slopes are increasing as we work back towards the point in question. All right, this last one here. I'm not going to draw it, but again, now we're using another point that's just to the right that's only 1,000th away, 1,000th of a second. Let's set up the difference quotient, which is very, very important. Because if an answer just appears without showing where it comes from, you're likely to not get points at all. And then one last time, I know this is probably getting boring, but I'm doing it for a very, very strict purpose. You get the idea of what's happening here. You might actually already see a limit emerging. You think it's 1? Let's see. If I insert one more 0 here and then hit enter, it gets 0.999. And yeah, I think you can kind of see it. So part E now, if you want to answer this question, based upon your mathematical evidence above, how fast is the graph changing at x equals 1? Does it appear to be approaching at least? 1, yeah. So it appears to be that the graph is at that instant, at x equals 1, it appears that at that exact instant, the graph is going up 1 unit for every 1 unit going to the right. But notice in the previous instance, it's going to be, what, faster or slower going up? Is the graph steeper or less steep to the left? It's faster, and immediately to the right, it's slower, okay? But it appears that there's a limiting value there on the secant line slopes. So we'll summarize that after lunch, and then we'll get back to the calculations, all right? Have a good lunch.